Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemistry, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Schur, and this month we're talking with Stuart Simmons about geothermal resources and cryptic volcanism. Stuart Simmons is a research professor at the Energy and Geoscience Institute at the University of Utah, where he focuses on crustal fluids, hydrothermal ore deposits, and geothermal energy. Stuart, welcome to Geochemistry.
Thanks. Nice to be here.
In addition to working in academia, you also run your own consulting firm, Hot Solutions Limited, which specializes in geothermal resource development and epithermal gold-silver systems. Considering these two paths, it's interesting to us here because you've navigated both paths through research and applied geoscience. Could you share a bit about your journey, what led you into these fields, and how you've balanced academia and industry to hopefully inspire some geochemists that are starting their own journeys?
Yeah, thanks. Looking in the rearview mirror, the history is shaped a lot by context. And when I was initially in grad school, I was going for a master's degree with the intention of getting a professional position in industry. And I chose economic geology because I thought it was relevant. I had spent 9 months as a mudlogger and did not find anything appealing about the oil and gas opportunities, even though the remuneration is pretty handsome. But I was my own person and I was going to do things my way. And I found the geology of mineral deposits to be so much more captivating. And in my master's work, I stumbled on fluid inclusions. And then when I finished my master's degree and I couldn't get a job, I went back and did a PhD. And probably as much as anything, there's a backstory here because in the 70s, the Club of Rome had it was a group of people with expert views on the future, had forecasted mineral shortages and a sharp need for geologists and engineers to help develop mines. And as it turned out, nothing could be further from the truth. So none of the forecasts proved correct. The 1980s were a wild and woolly time for geologists, particularly in the minerals industry. And a lot of our best geoscientists got rinsed out of the industry because really the 70s had overproduced too many geologists. And when the demand didn't turn out, it was what it was. Anyhow, when I finished my PhD, things hadn't changed very much, but I did have an opportunity to go to New Zealand to work on a project in Indonesia on ore deposits. And that looked really exciting. And I was particularly excited about the prospects of developing a research project in New Zealand because in the 1980s, there was a lot of really exciting research coming out about active gold and silver deposition in geothermal wells and surface pipe work. And there was a lot of commonality between the geology of the topovolcanic zone and the Fresnillo district in Zacatecas, Mexico, where I did my PhD. So I was looking for really fine-scale comparison of modern and ancient environments in a common geological setting. And I was successful in getting an AMIRA grant, which comes out of the Australian Minerals Industry Research Association. And that work really was a stepping stone into the world of geothermal and into the University of Auckland, where I was located for about 20 years. And following that, and just based on some frustrations, and now instead of seeing a challenging minerals industry, there was a real boom in mineral exploration starting in the early 2000s, and it looked very exciting. And I was having to pivot in terms of my teaching and research from geothermal back into minerals. And I just felt, and I was teaching a different set of students without going into details, but I felt I needed to be expert in as a teacher, that I needed some more real world experience. And I had tested the waters with respect to doing some consulting work, and it seemed possible. And so I stepped into the void and found that I had lots of clients who were interested in what I could offer for both geothermal and minerals exploration. And for a few years, that was my sole source of income. And that was really super. And only came back into academia because I got an invitation from the Colorado School of Mines to come and have a position there for a year as a visiting professor, a research professor. And 1 year's turned into 2 years. And then the University of Utah, the Energy and Geoscience Institute, asked me to come and join them. And so I said, okay. And with there, I had more flexibility and could retain some consulting. I've been involved with DOE contracts ever since I came to Salt Lake City for part of the year in 2013. And I continue to go back and forth between Salt Lake City and Auckland. Auckland is the family home. But anyhow, I spend a significant portion of the year out of Salt Lake City and still have a light load of consulting work.
That's so interesting. I'm speechless.
I'll say that I asked a senior colleague, a former professor of mine, 10, 15 years ago, I said, I'm looking to position myself where I've got like this part-time academic position. And he just said, good luck with that. They don't exist. And yet that's exactly where I've fallen into, and I pinch myself. I'm extremely fortunate. I take nothing for granted. It's a privilege to do the work that I do and to have the career that I've had, but none of it was forecasted.
I think that's also just a really good thing for people to continue to hear, especially young listeners, is that like you can't plan for anything and you just have to take opportunities as they come and not necessarily be grateful for scraps, but just everything builds on something that you've taken before. So just don't think that you're going to get your dream job right out of university. It's this windy path. And I think yours really shows similarly that you thought here you're going to go jump right into minerals, but then you wound up in a PhD because the markets were wrong.
So you're exactly right. And everybody has the same experience. This is not unique. I would just say there was a time, and I'm speaking, and I have to put myself back when I was young and looking for a career and really being so naive and poorly prepared to be thinking about like where there are opportunities. I would just say guidance counselors were just like inadequately prepared. I was like, make a plan. It's not a blueprint. It's just like a wish list. You don't even have the experience to know what you're planning for. And I was extremely fortunate to be offered the job in New Zealand as a postdoc. And when I went there, one of my professors at the University of Minnesota said, we'll never hear from you again. That's a dead end. And yet it was the best stepping stone. And I'm not the only person who's had that experience. I've got another colleague of my same age, and he did work in New Zealand, and he had the same advice. Don't go to New Zealand. We'll never hear from you again. You make of experiences individually. And I guess what I would say to young people is you should back yourself 110%. There are lots of opportunity for geoscientists, particularly today. Geoscience has never become more relevant to future prosperity as it is right now for multiple reasons. And I would just say we're going to put more pressure on how we utilize the upper 1,000 meters of the crust in this century in ways we didn't even imagine. And so we will continue to extract fluids and minerals, but we will start using the subsurface for storage. We already do. We will be continuing with our injection of fluids, and it's just going to intensify. Don't think it's going to ease off. And it may even be a refuge from energetic storms. So I just think it's never been better for geoscientists, and that they will be working more closely with engineers in looking forward to solving problems and actually finding the resources that sustain the prosperity looking forward. I know there's some pessimism sometimes about the outlook and the environment doesn't look so good, but the one thing you've got to see through the arc of human history is that they're very resilient species, and we've got a lot of information and we know how to process it. And so I think it's one that can be navigated. And I would look forward with optimism that there are solutions to the problems that we face today.
Very cool. I think we're going to have to take that and turn it on its head and ask what you brought us for tea time because, oh my gosh, you have so much optimism. I just would love to see what you consider gossip.
You'll find out shortly.
Okay. So, look, I think that was really helpful though, because I think at any stage in your career, you can become despondent. So, again, thanks for sharing your story because it all helps for sure. So, that said, and like I mentioned just before, it is now time for tea. The kettle's hot. It's time to spill.
So I guess I thought what I'm going to tell you about is not something that is not, I mean, I've talked about it before in a public arena, and I'm going to talk about it again because it is part of that story of my background. So what shaped, as much as anything, me staying in New Zealand was meeting my wife. But is it was meeting her that required me to stay in New Zealand. So I was smitten, besotted, and I knew almost as soon as I met her that I'd found the person I'd been looking for as a life partner. And we met in a pub. She was an adult student taking introductory geology class, and the TA for the course, or a teaching assistant tutor, was a close friend of mine, and he'd brought a bunch of students with him and we all went out for a drink. And I met my wife there, but and I knew almost as soon as I met her that she was the one she was the right person. And it's really amazing. It's worked out over 30 plus years. But I guess as much as anything, when I met her, I was on my way to Tasmania. So I didn't tell you that part. I was there to continue my research at codes at the University of Tasmania. And I didn't go. I called up the guy who had hired me and I said, okay, I'm not going. And as an only child with a solo mom or mother, she was terrified. She said, what are you doing? And really questioned my rationale. And it was only a few months later that I got the best teaching position I ever had, teaching in the Geothermal Institute at the University of Auckland. And for the next 10 years, I had the most extraordinary academic position where I was teaching adult students in the age of 25 to 35 who were geothermal scientists and engineers from developing nations. And we had 30 students in the classroom for a 9-month program. It was described as a postgraduate degree, or it would be a graduate degree. It was like a professional master's degree, but it just came with a diploma. But we took these students out of industry and we put them right back into industry. And I would say without that experience, I would have been, I would have had half the professional life that I did have. And it was all down to love.
That's beautiful. Oh.
Just to finish off that bit, that program was funded by the New Zealand government, and they terminated it there were other political factors in the realm. But when it was terminated in 2002, I struggled to find a niche at the University of Auckland because I felt so comfortable in that position. And I should say that it was a contract position. I never knew from the contracts were only from 1 to 3 years, so there was a lot of uncertainty. This wasn't a tenured position. And I got conditioned pretty early on about you just are as good as your last paycheck or your last paper or your last output, whatever compels people to keep you employed. And I never had that sinecure of tenure, never have in my career. That windy road we just talked about, I think you learn to build confidence in yourself to be able to find work. And I'll just say, I never knew where it was going to come from, but I've just been extraordinarily lucky.
And I think that's so powerful too, because When I think about, because everybody's always interested in my life, when I was doing my master's, a lot of the papers I was reading were Stuart's papers, actually, because he did quite a bit of epithermal research, and then he did a bunch of stuff using, we'll probably talk to them a bit later, but stuff using different equipment like Gegenbach bottles and stuff for volcanic research. But importantly, when you read through and somebody's name is always coming up in all these papers, you're just like, wow, this guy made it. And not that you didn't, but it's a much different story hearing it from you than you would think based on the literature that you've published over your career.
As much as anything, I would say since we're doing this deep dive, the people I worked with in the Geothermal Institute were exceptional,
Mm.
great collaborators. It was teamwork. And I would just say I knew it was never going to be replicated because I knew how academia runs in a normal sense. And this was an exceptional sense where engineers and scientists were co-teaching together. They were planning together, and we were field teaching together. And I just think about how universities are set up with engineering faculties and science faculties, and they create divisions and culture and how you approach problem solving. And I think I'm opposed to this process of teaching because I think it sends the wrong message. And I would say that I've always found it easier to talk to engineers than what I thought it was going to be. And I've almost made that kind of something that I feel like I specialize in, and I benefit from their company. I've learned so much about heat and mass transfer from talking with mechanical engineers that I wouldn't have otherwise gained from reading books or taking a class. And there's no better place to learn this other than a production steam field for geothermal energy because it's all real and applied, and there's a lot of tangible application. It's not like taking physical chemistry where somebody's talking about the Carnot cycle and or the second law of thermodynamics just seems very abstract.
Yeah.
Entropy remains an abstract concept to
Mm.
me, but enthalpy, by contrast, is something that's very real.
Sure.
And so the point I was getting to was that the people I was working with, and there's two people in particular, Patrick Brown and Kevin Brown, two Kiwis, they made all the difference. And they're my co-authors, and they provided the guidance which allowed me to take my enthusiasm and take the lead in synthesizing the data that we were obtaining. They were happy to facilitate and contribute to my own learning. And this was as a mid-career professional. Those papers you referred to, yeah, I benefited from really generous support.
Yeah. Wow. I look forward to talking about it more.
Yeah.
I want to thank you so much for the tea. I thought that was really beautiful and also very relevant. So thank you. But now getting to the topic at hand, you've enthusiastically brought your most recent research that we're going to base our discussion around, which is, and it surrounds the geochemistry of geothermal systems. And today we're going to be talking about why he and his co authors slowly uncovered mantle helium anomalies to put together a really fascinating story about bimodal volcanism in southwestern Utah in the United States. Before we got into the Q&A, could you talk about a bit about this research in general and starting with what is FORGE?
Yeah. FORGE is an acronym. It is sorry. It's a it's Field Observatory for Research in Geothermal Energy. And it was a program that was initiated by the U.S. Department of Energy back in, I think, 2012 or 2013. And the idea was to advance technologies that would support development of EGS research, EGS reservoirs and resources. EGS stands for Enhanced Geothermal System, and it really is an extension of a concept that was formulated in the 1970s called hot dry rock, which was a target for geothermal development, really driven by the Los Alamos National Lab scientists and engineers. And that that lasted through the early 90s, from the late 70s through the early 90s in various stages, but never quite reached its expected outcome, which was to be able to extract thermal energy from a volume of impermeable hot rock in the subsurface. And fast forward to 2012, 2013, DOE, the Geothermal Technologies Office, had a manager who had a lot of industry experience, particularly oil and gas industry experience, and helped frame this program. And so that's what I work on right now, and I've been lucky to do and since 2015. So this is basically investigating how to develop a hot dry rock resource in the subsurface. And it's different from a conventional geothermal resource where you're basically drilling wells to produce hot water and steam, and then separating the steam and piping that to a steam turbine. In this EGS scenario, you're drilling wells, you're drilling wells into volumes of hot rock that are poorly permeable, and you're injecting cold water to stimulate pre-existing fractures. Slightly different from fracking insofar as fracking is really includes the breakdown or the fracture propagation through unfractured rock. In this EGS scenario, when we're using stimulation where we are trying to take advantage of pre-existing fractures that are tight and opening them up, and hopefully because those planes of weakness are already existing, that they won't require the same high pressures and have the same risk to induce seismicity, that is, threatening induced seismicity. We like to think that there's a threshold. Below microseismicity, below a threshold of, say, magnitude 2 or magnitude 3 is beneficial. It's unfelt below the surface and has been used extensively for 20 plus years in developing unconventional resources, which is really underpinning all of the oil and gas production in the US today. And it's made the US the number one producer of hydrocarbons. And so that was another aspect of Forge, was it was supposed to be borrowing the technology from the oil and gas industry to apply it to geothermal energy, which obviously has the benefits of reduced greenhouse gas emissions that would benefit the climate. The other thing too is that this kind of technology, it doesn't have the same restrictive nature that, for example, geology plays in localizing conventional hydrothermal or geothermal resources. There is hot, dry rock everywhere at mid-crustal levels beneath or in continental land masses. So this is an environment that's widespread. Geothermal energy is everywhere. And it's a matter of being able to develop the technologies to extract that heat and imagine, and this was always what people looked at geothermal energy for, is it could be used in many countries and just for basic heat, just for heating homes, that would have benefits. Anyhow, this is a long-winded explanation as to what Forge is, but Forge is designed to advance these EGS technologies that involve stimulation, injection of cold water, production of hot water into volumes of hot, dry rock that are devoid of any native state fluids, and to advance the methodologies that will allow for sustainable geothermal production.
In answering this question, you went into my first question there, which was about just geothermal power in general. And I think really the only part that we didn't cover in that was the question as to why, at least the way I'm perceiving this, why it's not as widespread as we might think it could be now.
Yeah, so that's a really good question. And the promise imagined or aspired to back in the 70s has been really difficult to obtain. And the issue is that drilling is expensive, so testing concepts is difficult. Many countries have tried to develop this technology, and really significant push in the noughties in Australia. And they had a great resource in the Cooper Basin in the northeast part of South Australia, but it was 1,000 kilometers from Adelaide, which was going to be their main market. But the resource is still there, and there's probably still, it can be revisited. But I'll just say that it's a technology that's been investigated over and over and over again, and there have always been obstacles. And so to overcome this, DOE in their wisdom and really foresight, they made certain that there was generous funding to make certain that this project was going to go forward. And Southwest Utah was chosen on a competition, and there were 4 other sites that were part of the competition. I would just say there had been a lot of investigations back in the 1970s, which helped verify the heat flow and provided a degree of characterization that really none of the other sites had. The legacy data, as much as the ability to prove the opportunity with the pilot that the site met all the metrics. And also, just to point out that Los Alamos had been looking for other sites in the early 1980s. So their prime site was Fenton Hill, which is part of the Valles Caldera in northern New Mexico. But they actually picked this site as a top candidate for further hot, dry rock research, and they were dead. And all of the work we've advanced has confirmed that they were right about that. Should just say that right now there's a company called Fervo who is aggressively developing the resource in a commercial sphere. And if you're not familiar with Fervo, they are got very ambitious plans for development. And yeah, it's an exciting time. We're going to see how things go. But they're right next door to us. We share the same reservoir rocks. We are pushing the science side, and they're pushing the commercial side. And the realization of EGS technology may be on the cusp of significant breakthroughs.
That's cool. Especially Utah's going through a little bit of a population boom, so they got quite the market.
Yeah, that's right.
Little side thing for anybody not in America.
Yeah, that's right.
Coming back a little bit now to like straight geochem, maybe. I think generally everybody's familiar here what an isotope is, so we're not going to ask you to define an isotope. But what I'm curious here is what's the study of isotopes? How is it important to geothermal chemistry?
Yeah.
Yeah.
I'll just go back to referencing New Zealand geochemistry, because really much of hydrothermal geochemistry was that discipline or subdiscipline of geology and the geosciences was really formalized with the development of the Wairakei geothermal field in the North Island of New Zealand in the 1950s. And when that field was being developed, little was known about the nature of the resource, the origin of fluids, the origin of heat. It was assumed to be volcanic or magmatic, but it was really the success of Lardarello several decades earlier in Italy that New Zealand government and scientists were aware of, that provided a platform for even thinking about developing it. And then there were just needs for electricity in a small island nation remote from any other locale. And so with that, this pioneering effort to develop technologies around geothermal resources proved to be hugely successful. And it was a collaborative effort of science and engineering. And was recognized early on that mineral deposition was going to be really critical to manage, because wells were going to scale up. And so chemists were brought in, not geochemists, chemists. And they set up experimental labs. They had the field facilities. They had the analytical facilities. And the outcome of that was a definition of analytes that were relevant to understanding processes, not just running through the periodic table, picking up on sodium, potassium, calcium, magnesium, boron, silica, chloride, bicarbonate, sulfate as like prime important candidates. And if you're worried about the environment, arsenic too. At the same time, oxygen and hydrogen isotopes. Harmon Craig was advancing this in the early 1960s, the idea of being able to determine provenance of waters using the stable isotope compositions of oxygen and hydrogen. And the New Zealand geochemists were acutely aware of that benefit. And so they had the first mass spectrometer in the Southern Hemisphere came into DSIR. That was the Department of Scientific Industrial Research, which preceded the modern day science organizations in New Zealand. But there they had a division of nuclear science and they had a mass spectrometer and they were learning isotope geochemistry and they were making great contributions to our understanding of hydrothermal systems, how they operated, and contributing to the broader understanding of the geological context, the hydrological context, and really much of our models are based on work that was done out of that research. So from the 1960s, oxygen and hydrogen isotopes were being regularly analyzed, despite it was pretty expensive, but they had the machine to be able to do it, so they were doing it. And they had very talented scientists. And they were being sent off to Europe to get trained, largely the UK, or they were being hired from Europe and coming to New Zealand. So a couple of people, Werner Gickenbach and Mike Stuart, wrote a classic paper on the use of oxygen and hydrogen isotopes in the early 1980s. It probably has just disappeared off the radar screen, but there isn't a better study and testament to the potency of being able to track hydrothermal heat and mass transfer between the steam phase and the water phase, and just a beautiful exposition about how to really understand heat flow, hydrothermal processes using these isotopes. Of course, sorry, I'm going off on the hydrothermal context, but at the same time, oxygen hydrogen isotopes were finding many applications through the geosciences, from everything from igneous petrology through to groundwater hydrology. The abundance of these elements in rocks and minerals and groundwaters just made them relevant for study. Probably drifted off the subject there a little bit, but
I love it. It's all about drifting and rabbit holes and tangents. We talked quite a bit about our standard oxygen, hydrogen, but do you use radiogenic isotopes at all? And if so,
yeah, typically radiogenic isotopes are used for dating, and whether it be carbon or argon, potassium argon, or any of the other strontium, neodymium, samarium, the whole gambit. In the geothermal realm, the key isotope systems, apart from oxygen and hydrogen, carbon has been extensively explored, and I think we might talk about that a little bit later on, but the problem with carbon is it's a little bit ambiguous. So let me just back up. So one of the benefits of looking at isotopes is that you can identify the provenance of the element and the media to which that isotope composition is attached, say like for water or for a mineral or for, say, a rock. And particularly for waters, we know we can distinguish meteoric waters from magmatic waters, and that became very relevant to geothermal exploration. Now, it's probably only been in the last 20 years that stable isotopes have been routinely analyzed in geothermal projects. But I mentioned Waitaki initially. When I say routinely, maybe once a year, every well's being sampled, and there's a multi-decadal time series data set to allow you to track changes in oxygen, hydrogen isotopes. Going back earlier, it was really too expensive to afford that, so there would be one-off studies, and it would just be applied to different areas. Additionally, so to answer your question, helium isotopes proved to be very interesting and have a relevant application in geothermal resource exploration. To back up, helium isotopes really came into their own in the late 1970s with the discovery of submarine hydrothermal activity. And the oceanographers were discovering basically helium-enriched columns of deep ocean seawater and didn't know where they were coming from. And by surveying these, let's say, helium endowments or plumes, they were able to trace them back to the black smokers that we now understand today as being characteristic of mid-oceanic ridges. And really, that's how the anomalous heat flow and hydrothermal activity was discovered. So they were the smart people at the Scripps Institute of Oceanography in La Jolla, California, Harmon Craig and others were exploring what helium would mean in terms of its isotopes. And they put together the sort of interpretive framework. And you could see that there was three major provenances for helium isotopes: the mantle, the atmosphere, and the crust. And when I'm talking about the crust, I'm talking mostly about continental crust, not seafloor crust. And that there was large separation in helium isotope ratios between air, which was midpoint, and the mantle, which was 10 times or 8 to 10 times higher than air. And then there's the crustal helium, which is like 10 to 100 times smaller than the atmospheric ratio. And this ratio is helium-3 to helium-4. By the late 1980s, companies like Unocal, who were doing global geothermal exploration, used helium isotopes on all the hot springs that they were sampling for other chemical analytes. This was like one of the earliest applications of helium isotopes to exploration. We applied it at Utah Forge as part of a regional program that we got some funding. A colleague of mine, Stephen Kirby, at the Utah Geological Survey, we pitched to our colleagues who had funding that we thought that characterization of the hot springs needed to be reinvestigated. It had been done 40 years earlier. And we wanted to include with that the noble gases, because there happens to be a noble gas lab here at the University of Utah run by Kip Solomon. And so we could get the analyses locally, and incrementally, we built up a picture of the application of helium isotopes here, and then stumbled on really what was the anomaly that we described in this paper that you referred to, which was a very large endowment of mantle helium in cold groundwater. Previously, people were expecting it in hot springs, hot waters, no problem. So you had thermal energy being transferred with a signature in the helium isotope ratio indicating some deep mantle inputs. And isn't that amazing that like a hot spring that you can see on the surface has this verifiable signature from such a deep part of the earth that's inaccessible? We're talking 25, 30 kilometers depth. It's absolutely extraordinary. And yet you can see it all around the Pacific Rim in volcanic systems. You can see it in Iceland. You can see it in Hawaii. Almost any place where there's volcanic activity, this mantle helium signature is found in volcanic emanations. So to find it in hydrothermal emanations just seals the deal and tells you how important magmas are to driving that hydrothermal activity. Did I answer your question?
You did. The thing is that, and I'm going to leave this in for the listeners, you have skipped between probably 5 of them, but in such a fluid way. But I'm just checking them because to see if there's something that I want to go back to. But no, it was extremely fluid, I found. Pun maybe intended there. Actually, a little side quest here. The mantle helium, where's the helium occurring in the mantle? What's its
Right.
phase?
Okay. Yeah. Good question. Helium-3 is a primordial isotope. It's part of nuclear synthesis. That was an original endowed isotope. Helium-4 is an alpha particle. So we know that very well from the decay of uranium and thorium. And what keeps the planet thermally alive, and really what keeps us alive on the surface, all organisms, is the heat flow and the sustained existence of an atmospheric envelope of gas, which we depend on. It acts as a shield from cosmic radiation, and it also, of course, is the air that we breathe for life. The helium-4 is a byproduct of radioactive decay. And so it's obviously elements like uranium and thorium are enriched in the crust. And so there's a lot of radiogenic helium just produced there, but also in the deeper Earth's interior and the mantle.
All right, love that. Think we're staying on isotopes, which it's funny. If this was me probably a year and a half ago, I would have feared this conversation now that we've been talking about half an hour about isotopes. But I'm just like, tell me more about isotopes. I feel much more empowered to talk about isotope geochemistry, at least ask questions about it. But coming back, we talked in the beginning a little bit on carbon, but I want to come back to it. I was wondering how carbon-13 values in these dissolved inorganic carbon contributes to identifying sources of carbon and their interactions with a geothermal system.
Yeah, carbon is relevant because, of course, apart from water, the other main constituent that comes off of magmas is carbon dioxide. And volcanoes emit a lot of significant amounts of CO2. And people have been studying this, volcanologists in particular, for the last 10 plus years or so, because they want to know what's the natural contribution of carbon dioxide to the atmosphere to be able to distinguish it from the anthropogenic effects. But going back probably to the 1950s in the University of Chicago, where a lot of nuclear chemistry was being developed, the systematics around carbon isotopes have been framed. And I think with the study of hydrothermal ore deposits in the 70s, there were a lot of people looking at carbon isotopes. It was routinely done for theses that were studying the geochemistry of these occurrences, but really quite ambiguous in terms of resolving precise origins. But there's a lot of evidence pointing to a mantle origin, which is in the realm of about -5 plus or -2 per mel delta C13. So that's the carbon-13 to carbon-12 ratio. But air has, I think it's got an isotopic composition of -7. So it directly overlaps. And a paper that I wrote on Roosevelt Hot Springs, editor said, and I made the inference. So this is the predecessor paper to the one we're talking about, but it's referenced, and it looks specifically at Roosevelt Hot Springs, and it shows how oxygen, hydrogen, carbon, and helium isotopes were used to characterize the fluids in that system. But I said that I thought that this was the mantle carbon, and it was pointed out to me that how do you know it's not from the air? And I guess at that point you say there's 8,000 ppm carbon dioxide in the deep fluid. I don't think this would be fantastic for knowledge if we could say that hydrothermal fluids sequestered atmospheric CO2.
Yeah.
There's a bit of context here that's relevant. This is where you can get too specialized and start thinking about too narrowly about what you're studying. You obviously always have to understand the broader picture, and we get clues to formulate our interpretations from multiple lines of evidence, and it could be multiple lines of geochemical evidence.
Yeah.
And that's I have to say this. What's so exciting about hydrothermal fluid chemistry in an active environment is that you have so many different parameters. Silica tells you something really important. Magnesium tells you something. Sodium potassium ratios tell you something. Oxygen and hydrogen isotopes tell you something. Helium, they all tell you something different. And it's, oh my gosh, it's like I got a Rubik's Cube of different parameters here to play with. And they all are going to provide a window into, if you like, the soul of this hydrothermal system.
Oh, amen. Can we get an amen, listeners? Oh, I love it. So cool. I never thought I'd find isotopes so cool.
I have to agree, but my involvement with helium isotopes goes back to my PhD.
Okay.
So the second paper I ever wrote and was published was on helium isotopes of inclusion fluids in Peruvian polymetallic ore deposits.
Okay.
And I was extraordinarily lucky that it got published in Nature. But there was a lot of work being done on helium isotopes at the time. And I was also extremely fortunate. So I did my PhD at the University of Minnesota, And there's a guy in the physics department there. His name is Al Near. And for people who are familiar with isotope geochemistry will know the name because he is the grandfather of modern mass spectroscopy. And it was in his lab going back to before World War II that he was building mass spectrometers just with a glass blower and himself and going through mapping out basically the isotope abundances of many of the elements in the periodic table and finding applications for them. So I got introduced to him as a PhD student. It was going to be a novel part of my PhD thesis to look at the helium isotopes of inclusion fluids. I had no knowledge about this stuff, and I had no background, but I was a willing subject, and I did the characterization of the fluid inclusions, and then got to go into the lab, and this guy was the nicest guy in the world. And he was so generous, and his technician equally, and they just helped me through it. And we tried to look for evidence of mantle helium in inclusion fluids from epithermal deposits, and thought in the end we identified them, which was important to my supervisor, who was a strong magmatist, felt like there was a one-to-one relationship between magmatic intrusions and hydrothermal ore mineralization. And I think he's probably right in many cases, but not exclusively. But the thing is that I abandoned that and I got more interested in the active environment, but I didn't have a laboratory that I could utilize. So it's only coming back to the US and being at the University of Utah that the opportunity presented itself. And I relished it. And I'm coming into it after not really being fully immersed in it since the 80s, early 90s. So much had advanced, so much more work published, so much more just to work through. So one of the biggest impediments to the kind of research is just reading through reams and reams of papers, which establish your scholarly credentials when you're trying to get peer-reviewed publications accepted. And it's challenging, but it's very rewarding.
I love it. This is so cool. I love doing these interviews because it's also a combination of learning new things and then also talking about pieces of history that I wouldn't have never known otherwise. Yeah. This guy,
So
Dr. Neer.
Al Near, you can go and look. He won. Harmon Craig was his. What do they call it? He gave the. Oh, sorry. Don't grow old. That's my motto.
This happens to me all the time, especially after 8 p.m. You take your time. Have your
Look
moment.
here. What do they call? Oh, citationist. Harmon
Yeah.
Craig was Al Near's citationist for the Goldschmidt medal.
Oh, okay.
And it's worth reading because Harmon Craig said, oh, and he was a very young upstart grad student at the University of Chicago. And he said, oh, yeah, I went up to Minnesota. I was told to go up there and check out this guy Near's lab. And I examined his equipment and like down to the tube and all the various electrical componentry. It was all the same as what we had in our lab. And I thought, who is this guy? He's just stolen our design. And it was framed in that kind of tone that this was intellectual property that had been stolen from the University of Chicago. And it was only later that he learned that Al Near had designed all this stuff and given it to the University of Chicago. I can't think of who Harmon Craig's supervisor was right off the top of my head, but a very famous isotope chemist who really was responsible for much of the great work that was developed out of the University of Chicago. You got to edit that out because I'll look stupid. He's very famous. But the citation is really, you should just check it out. It's in Geochemica if you've got access to it, or I'll send it to you because it's
Yeah,
really insightful from a historical perspective. And it gets you a little bit behind the scenes in terms of the personalities.
for
I'll
sure.
just say that there was so I was lucky to work with him. I was lucky to work with Werner Giggenbach. I was lucky to at least know and be in communication with a guy like Dick Henley, in addition to the other New Zealand geoscientists that I worked with, who were all extremely generous and so insightful. And it wasn't just the geochemists, because there was a broader community of geologists working in an active environment. It's nothing like being on a plate boundary. There's so many different things going on. It's really super exciting.
Yeah.
The interaction of tectonism, magmatism, and hydrothermal fluids. It's not just the North Island. The South Island is endowed with hot springs too, and additional hydrothermal ore deposits that developed in a metamorphic environment, orogenic
Right.
terrain.
Look, so let's switch some gears. I'm interested now to chat about you with how your research, which I don't think for our listeners, I don't think I've ever said the title. It's the title of the article is Formation of a Large Cold Groundwater Mantle Helium Anomaly and High Temperature Geothermal Resources in Response to Bimodal Magmatism near the Roosevelt Hot Springs and Utah Forge, Milford Valley, Southwest Utah. I wanted to delve into how this research integrated geochemical, isotopic, and geophysical data and was able to suggest that there is in actuality an existence of a large concealed magmatic body beneath the mineral mountains. So, what specific evidence, including all three, we can even talk about geophysics here, allowed you to infer the presence of this body? And how really did you start to tie in all these lines of evidence together?
Yeah. First, I'm going to apologize for that very long-winded title. I had probably multiple versions of the title. Actually, can I just back up and talk about writing a paper?
Yes. Yes. This is all about learning, this
Yeah,
podcast. Tell
so
us.
so I have to say, I want the people who really interested in trying to get their research published to understand that, unlike at least what I was taught, was like, and when you write a paper, you sit down, you write an outline, and then you write it, and it just materializes like out of thin air. And that there's just flowing fluid logic, and that maybe in a long weekend, you might be able to put something together that will pass muster for a peer-reviewed journal. Okay, I'm
Effortless.
exaggerating. I'm,
Yeah,
I'm
yeah, yeah.
exaggerating, but I think that old adage, the devil's in the detail, is almost like an understatement, a woeful understatement of what writing is all about when you're trying to convey your data. And I think, as much as anything, I personally, I'm compelled, if I can put together a story. I'm not publishing just to publish data. I'm publishing because I think there's a story and an interpretation worth telling. And that's another thing that's so exciting about geology. The greatest stories never told, all waiting there to be revealed. And this study was just an example. When we first embarked on our work, we knew that was a mantle helium signature at Roosevelt Hot Springs. And that's all we knew. And so this is a really compact field. The data had been acquired before, no, it had been acquired since the production field had been established in the early 1980s. But it was convincing and didn't really need to be reinvestigated. But we had a chance to sample it and reinvestigate it, and it was the same as what had been reported in the 80s. Nothing too remarkable there, but it provided us, I guess, a benchmark, a geochemical benchmark in terms of what we might expect for a high temperature hydrothermal fluid. And what needs to be appreciated is that Roosevelt Hot Springs is one of the hottest hydrothermal systems in the Basin and Range province. It has all the hallmarks of a magma related hydrothermal system like Waitaki or any one of 100 hydrothermal systems in the Pacific Rim associated with volcanic edifices. And yet in Roosevelt Hot Springs and in the Milford Valley, there's just some tiny rhyolite domes in the mineral mountains that are over 500,000 years old. And they've recently just been redated and confirming the earlier dates. So they range from 500,000 to 0.9 million years in age, which is on the old side for surface expression of magmatism in the vicinity of magma-related hydrothermal activity. So like in the central volcanic zone and in Yellowstone and in Iceland, there would all be much younger eruptions, maybe only 10 to 20,000 years in age, that would be in the vicinity of the hydrothermal system, providing testament to the existence of recent melt bodies in the subsurface acting as a heat engine for hydrothermal convection. We were out looking at groundwaters west of Roosevelt Hot Springs, primarily because we also knew since the 1980s that there was an outflow plume from this hydrothermal system that was confined to a shallow aquifer in the alluvial gravels, which filled the valley. Just beneath the surface, just a few hundred feet deep, the water table. And so below that, we're getting into these shallow aquifers. And you could see just on the groundwater chemistry, this outflow plume. And it was first described back in the 1980s. And then Stephen Kirby, my collaborator, co-author, had done work on it as well as part of the Forge project, the early part of the Forge project. And we sampled a couple of groundwater wells to the west of the Forge project. I want to say they were about 3 or 4 kilometers to the west. And to our surprise, they had mantle helium signatures. And they looked the same as Roosevelt Hot Springs. It was about 2 times the atmospheric value. And I'm talking with others. The initial interpretation was this is just part of this outflow plume and nothing to be really interested in. But we were curious enough, we wanted to validate, and there were a lot of shallow wells that had been drilled in the middle of the valley looking for groundwater. And I guess what people have to realize that in this part of the world, in this part of the western US, and particularly within the basin and range, basin fill alluvium is extensively utilized for irrigation, for growing alfalfa through many of the valleys of western Utah and Nevada. The wells were there, we just needed to pump them to sample them. So we incrementally built up this picture, and over time, we could see that there was like mantle helium. We could trace out the extent of this mantle helium anomaly. And it wasn't until 2020, 2021 that we actually got what we thought was total closure on the signature. And we went back and did some repeat analysis. You look at the table, you can see that there are several wells that were validated by repeat measurements. We were interested to see if there was any temporal change. And we just wanted to verify things. I was a bit conservative, and it seemed too amazing. And I needed to just be sure that of what we were going to commit ourselves to in terms of interpretation. But by carefully comparing the groundwater chemistry with the noble gas signature, we could see clearly that there was a separate source of mantle helium, totally unrelated to Roosevelt Hot Springs. And we could separate it and distinguish it from the outflow plume. And as a consequence of all this work, we really provided definition to the outflow plume. We discovered another groundwater type, which is still enigmatic in terms of its origin. And I'll just say, just to back up for context, this outflow plume has a high TDS, so that's pretty saline, it's non-potable, and it's easy to distinguish from the fresh waters that are potable and that are produced largely to water stock, but are also used in a nearby town for water supply. Sorry, I'm getting a little hoarse here, but the
Take a
enthusiasm.
break. Yeah, I know.
Yeah,
Take a break. Have a drink.
I should, but I'm going to just suck on this mint for a second. The main way we identified the separate source of mantle helium was by careful analysis and examination of the geospatial patterns of the groundwater compositions versus the noble gas compositions. And by seeing discontinuities between the different types of waters and this helium isotope signature, which I'll tell you what, the interesting thing about it was so consistently uniform. So the helium 3-4 ratio was consistently between about 1.9 and 2.6. Didn't change at all, and overlapped with that of Roosevelt Hot Springs. And I had some colleagues who I'd talk about what we were finding, and they continue to say, it's just outflow. But when we had the advantage that we had some water wells, a singular water with a mantle helium signature that was on the other side of the hydraulic gradient of the valley. Most of the project and sample sites were on the east side of north-south oriented valley. And so the hydraulic gradient dipped towards the center of the basin and in a westerly direction. But then we had a well on the other side of that hydraulic gradient that actually had a easterly direction, and it couldn't have been outflow. And so the physical context, along with the chemistry, provided definition that there was a separate source of mantle helium. And then it was like, okay, so how do we explain that? And so there was another colleague that was on the Forge project, Phil Wanamaker, who sadly passed away a couple of years ago, but he is MT specialist. So MT stands for magnetotelluric resistivity. And so he had just completed his survey work. And for those that are not familiar with this, you can get an image that is interpreted to be the resistivity patterns or structure of the crust down into the upper mantle. And the thing is that with resistivity, you're looking at differences between resistive materials and conductive materials. And conductive materials are things like pore waters or hydrothermal fluids and watery magmas, whereas resistive materials are dry rock. And there was several orders of magnitude differences in the resistivity. And it's as good as it gets in terms of really being able to see intrusion of deep mantle melts into the lower crust. And so we referenced that, and we were aware of that work. And I talk to Phil all the time. We separately, he's always been interested in mantle helium, and it was a natural collaboration, but we had talked about writing a paper together, and sadly, he just passed away before we could get around to doing that. And he actually hadn't published all of his work formally. So we had to cobble together stuff that he had published and put on file. But he's almost the silent third author, and we acknowledge him greatly for his contributions. So another colleague, Rick Alice, had written a paper, as a heat flow specialist, had written a paper on basically the thermal structure and identifying really that there's two separate domains that are part of this large geothermal system. In one part of the system, east of a north-south trending fault called the Opal Mound Fault, is the Roosevelt Hot Springs hydrothermal system. So there in crystalline granitic rock that's been fractured, you have heat transfer by convection. And as I mentioned, we had the geochemical evidence that this was being driven by the intrusion of magma. To the west of the Opal Mound Fault, there's no evidence of convection. There's a conductive temperature gradient. They're quite distinct, easy to differentiate. Conductive gradients are linear, and they act this other benefit because of their linearity is that you can project them for a long ways. And so in a paper that Rick had written in 2019, it was a compendium of papers on knowledge gained from investigations on the Forge site, he could project it down to 7, 8, 9 kilometers depth. And the geothermal is 70 degrees C per kilometer, and 70 times 10 is 700 degrees. Okay, at 10 kilometers depth, you're getting magmatic temperatures. We think that conceptually, for convective hydrothermal systems, a depth of 10 kilometers seems about right for where intrusions that are heat engines might be stalling out. But that's largely based on knowing where the brittle ductile transition is in active tectonic regimes. And I'm referencing really work that's been done in New Zealand. There's inadequate knowledge, and I certainly don't have all the references to, let's just say, the rest of the Circum-Pacific or other well-characterized volcanic belts. But here again, just at Utah Forge, projecting this conductive gradient downwards, you could see, right, you're getting into the region where partial melting might start initiating. And certainly you only have to go a few kilometers deeper and you're in the zone. Rick didn't quite take it to the point of saying, okay, this is magmatic, but he said he basically was laying the stepping stones, which just provided us with real need to investigate this further as a third line of evidence for a magmatic region. And there's been other data that have been collected by seismologists too that showed that based on different differences in shear wave velocity, that there were probably regions of partial melt. There was a slowing of the propagation of the seismic waves and seismic energy. So there was other lines of evidence, but this geothermal in particular had the unique quality that because Rick had framed it all. It says, okay, this is the zone of conductive heat transfer. It covers an area of about 45 kilometer square area. This is the volume of rock that in which this heat has accumulated. And it just was for us to apply a very simple calculation, which for reasons I don't know why he didn't do it, but he could have. Anyhow, we did it. And we were able to calculate the anomalous heat stored in the rock over and above the background geotherm and use that to relate it to the amount of thermal energy that's released upon solidification of both a granite or a basalt. And from that, we were able to really provide 3 lines of evidence indicating not only that there was a magmatic source of helium, mantle helium, but we could even make the inferences, one, that this signature that was only about 2 times the atmospheric value was really diluted mantle helium, and it was diluted by incorporation of radiogenic helium, that is helium-4. So there was only a component or a proportion of the helium that was truly of mantle origin. There was a lot of added helium that came from the crust. And so that told us that it probably wasn't a mafic magma, but that it was probably a magma that involved a partial melt of the crust. And since rhyolite had erupted historically or geologically in the Mineral Mountains, it was pretty simple to say, right, okay, this is a silicic or felsic magma that is the source for this helium. But we knew we were in a terrain with bimodal magmatism. Outside of the Mineral Mountains, all the other volcanic centers are mafic, up into the severe desert and down to St. George, which is in the southwest corner of Utah. There are isolated occurrences of mafic volcanic centers, and some of them very young. And it extends, that sort of region of sporadic volcanism extends into northern Arizona. So that was known, and there's even been isotopic studies to characterize the helium isotope signatures of those mafic magmas. So we knew what that was. It was about 5 or 6 times the atmospheric value. And so that is not true, let's say, morb type mantle, but another type of mantle material referred to as subcontinental mantle lithosphere. So it's a little bit contaminated, but so the end member composition there is about 6 times the atmospheric value. So that would be more like a pristine mantle signature. Coming back to the different lines of evidence, we had the helium isotopes, felsic melt in the subsurface. We also had Phil's MT resistivity structure, from which we could see the upper crust, and it lights up locally where you can say, oh yeah, that looks probably a mafic melt region, and it just happens to be right underneath Roosevelt Hot Springs. It doesn't really get any better than that in terms of spatial correlation. But when we calculated the total volume of recently solidified melt, it wasn't a small number. It was over 400 cubic kilometers, and that's a large region. And so if we just took it to being a region 2 kilometers thick, it spread over the same large region that we were seeing mantle helium in the cold groundwaters, which was over 200 kilometer square area. Okay, like it's a big stretch to take a shallow mantle helium signature in cold groundwaters and try and correlate that directly beneath that high level to the base of the crust or into the lower crust and say there's going to be a one-to-one spatial correlation. And certainly the resistivity model provided clues for the potential for some other fluid conduits that were perhaps terminating once they got to shallow level into where the basin fill was predominant. So they may have been blind to the surface and concealed beneath maybe several kilometers of sedimentary infill. And so we were able to put together this model for how we were basically seeing at least two separate flow paths transecting the crust that was providing egress for mantle source helium to the surface. One was related to hydrothermal activity in the upper crust, that's Roosevelt Hot Springs, and the other was a cold groundwater regime. And the only questions really that remained unanswered was how was that helium moving into the cold groundwater regime? And just by doing the background reading, and there's one paper by Werner Giggenbach, who I referred to earlier. Really, the guy was so insightful about how to apply geochemistry to a range of hydrothermal volcanic processes. If the listeners are not aware of his work, if there's somebody whose papers I would recommend going back into the 80s and 90s, because he passed away in 1996. He was a giant. And I think probably people think, it's over 10 years old. Actually, it's over 2 years old, so it's probably irrelevant. And it was so fundamental. And his insights have stood the test of time and are really relevant. But anyhow, getting back, how does helium get into the cold groundwater regime? It's tricky. And one of the questions that we had was, is this possibly a geochemical clue to a concealed geothermal resource in an area that nobody even knew that there might be some promising developments? Anyhow, that's where we left it. And I guess we put together a synoptic model in trying to really get an understanding of the magmatic system and the helium fluid flow system and its relationship to hydrothermal activity and the distribution of thermal energy between this conductive regime and the convective regime. And what became clear is that we're probably in the conductive regime, we are looking at a thermal aureole to this large magmatic intrusion. And really, Utah Forge is taking advantage of that.
There's so much that just happened there, but I feel like two questions that maybe that will at least help me. Number one, I think you already answered, which is number one, the implications of having such a large convecting system. What does that have for the geothermal potential in the area? And number two, what does this mean in terms of potential volcanism in an area that one does not suspect that there is even volcanism?
Yeah. Oh, such good questions. And they take me back through my thought process in trying to put this paper together and what I needed to express and what I didn't need to express. There's another, sorry, I'm going to reference New Zealand geoscientist.
Perfect.
There's a guy named Mike Isaacs, who won't feature in anybody's list of must-read papers, but a really insightful geologist who was a manager of GNS, which is basically the Crown Research Institute in New Zealand that manages geological research and outputs. And he always had this kind of mantra in terms of what he was selling to clients. And he wasn't the sales guy, he was a manager, but he knew that the applied benefits of geoscience was either to hazards or resources. And he used to say what the two driving influences on the course of civilization are fear and greed. And geologists occupy both.
I like that.
And so there's a large group of geologists in New Zealand that are dedicated to hazards, so whether they be volcanic or seismic, and then a group looking at resources. So gold and geothermal energy being prime amongst them, but they also used to do coal and other basic materials that would be mined. So anyhow, in coming back to writing this paper, I was thinking about, I hope somebody doesn't pick up on this, that there's just like something, some imminent eruption.
The headline that you'll find.
Yeah.
Yeah. USA Today.
Yeah. Yeah. And are you familiar with the eruption of Mount Pinatubo in the 1990s in the Philippines?
Oh, sulfate saturated magma. Of course I am.
Yes. Okay. So do you know that Mount Pinatubo was a geothermal prospect of the Philippine National Oil Company?
I could
And
imagine. Yeah.
they
Okay.
drilled 3 wells in the late 1980s prior to the eruption, and then were blamed for stimulating the eruption. And you'll like this because what they found in their wells were acid magmatic brines, and they abandoned that project area. And it's not the only area that the Filipinos have drilled that contain magmatic brines that are, you just can't engineer them, the production side of them, but they're scientifically very interesting.
Yeah.
Anyhow, yeah, you live long enough, you read the stuff, you become aware of the fact that people might inadvertently maybe just extend an interpretation a little bit too far or beyond what the author intended.
Mm.
And so far it hasn't gone in that direction. But I to be honest, this is all part of a continuum. It's an end member. You ask what I think I talk about in the paper and a little bit, and I know from our previous conversation, it overlaps with Yellowstone,
Yeah.
and but there's a difference in scale
Mm.
and there's a difference in output. But apart from that, they share a lot of commonality. And what I would say is that the magma supply that's providing the heat and the helium at the surface is the predominant expression of this magmatic system. And the magmas have just stalled out, and most likely just because it's trickle feed. It's not a supercharged plume of hot mantle material that's flowing up to the base
Right.
of the crust here. And you get that impression just by looking at the small cones and the restricted extents of basaltic lavas around all these isolated centers that I mentioned earlier.
That's a
They give
really
you
good
some
point.
clues. Yeah, so they
Yeah.
give you some clues about
Yeah.
scale. And but here's the other thing: if this magma is trapped at deep level, and as I already referenced, the evidence of a silicic or a felsic magma, that takes time to develop. And so heat has to be transferred from mafic magma to a felsic or to a felsic rock. And we assume it's the granitic rock that we can see in the mineral mountains and is also forming the reservoir. Perfect composition, sialic material, and that it would have a melting temperature of 800, 900 degrees C, and that this is going to form pockets of partial melt that are going to be conceivably distributed. We don't know anything about the details of the geometry. It's really just speculation to even infer anything about it, but it's probably a complex of sills and dikes. And that's about as much as you could say about it without really overinterpreting what you can make of the data that has been measured on the surface.
Oh, that's so
So,
cool.
so there's another piece to this story
I
that
love it.
has not come out yet. I tell you, there there's so many surprises. We've only talked about the regional picture. I've not talked about anything about what we've discovered over the last 3 years on the reservoir, which is equally as captivating. And I'll be just writing a paper for presentation at the Stanford Geothermal Workshop, which is just coming up in a couple of weeks' time. But the contrary to what was published in that paper, we now know that there is mantle helium and probably mantle carbon dioxide infiltrating the granitic rocks in which Utah Forge is hosted. And so we have detected it in the produced waters from circulation tests that we just did in August this year. So hot off the press, not even really in the public domain. And so most of the results look just like everything else that we've measured between 2 and 2.5, the atmospheric value. But one value is over 5 times the atmospheric value. And that I've just dropped off a sample to get reanalyzed, a duplicate. And that's another lesson. When you're doing this kind of field sampling, always take a duplicate sample to
Yeah,
check your analytical result. Don't
for sure.
rely on one. So anyhow, a duplicate. So I'm going to cross check that. And oh my gosh, that would be, that would implicate a source from a mafic magma, not a felsic magma. That's new. And that would all have come about from the stimulation. So I'm hopeful that your listeners are really just young geochemists who won't really know how to put this into context. Don't tell your parents who are also geoscientists, perhaps volcanologists. But anyhow, it's very exciting and expect the unexpected. And as much as anything, this is the great thing about field science. And it's what's so challenging in the research environment is if I knew what I knew now, could I have gotten an NSF grant to do this work? Almost assuredly. Would I have had the knowledge and insight at the start or even midstream to have gotten that kind of funding? I don't know.
Mm.
And that's a challenge as well for institutions that are funding science, particularly field science. It's hard to know what you're going to encounter. And of course, you rely on the groups and individuals who have strong track records. But anyhow, there's just so much to discover out there. And I would say that amongst the things that cross my mind in understanding this is okay, so I was anticipating that really we would see perhaps a radiogenic signal, a strong crustal signal, so less than the atmospheric value in our produced fluids. We got the opposite. That really tells us that although there may not be any aqueous fluids coming or circulating in this volume of rock, there definitely are gases that are permeating it. And they have very low viscosity. And so there's no reason, if you just know Darcian controls on fluid flow, there's a viscosity term. And the controls that influence the flux of gas through fractured rock, even if they're really tight and impermeable to waters, could be permeable to gas. We seem to be detecting that.
I just watched an entire presentation, I think in December, about a karst geologist at the USGS who just bashed on Darcy's Law the entire time. It was fascinating.
So this starts giving us clues about how gases might actually be transmitted through the crust because the Utah forge conditions actually replicate conditions at 10 kilometers depth, not 3 kilometers depth.
Oh.
So if we want to go and look at what average continental crust looks like and think about how
Mm.
gases might infiltrate that crust, if there's a source and supply of gaseous constituents, there's no reason why they couldn't possibly break through that mid-crustal level. So I'm just saying this has relevance to thinking about the what separates a magmatic intrusion from the overlying convective hydrothermal system, because it's hard to believe that magma is in direct contact with water. Instead, it's always conceived conceptually that there is some solid barrier
Yeah.
of sort of crystallized intrusion through which, and Werner was talking about this back in the 90s, early 90s. He saw the problem. He couldn't quite understand how gases were infiltrating into the base of convection cells, but he could see in meteoric water dominated hydrothermal systems all these magmatic gases, very well constrained, and maybe even the source of chloride, which is ubiquitous in hydrothermal fluids around the
Yeah.
world.
Well,
I think I've overwhelmed you. I've overwhelmed myself. I can't believe you've given me this opportunity for this total download of what really has been one of the most captivating things I've worked on. And there's many facets to it, but so sorry, another digression here. My emotional response in just trying to describe this to you speaks as much to the emotional energy required to pursue science as it does anything else. And for those of us who sometimes don't have all, let's say, let's just say my teachers, probably right up through grad school, might have been a little bit amazed at the work that I've achieved subsequent to that time. And I would say to them that they never designed a test that revealed my genius or insights. And their inability to see my abilities was more their failure than mine. But I was doing as best I could to conceal it for a while too. So there was some personal components. But I would just say, like, it when you don't come in with all the intellectual faculties, the very bright scientists who do work, you rely on emotional energy to drive you, to take you to the caliber required. And I bank on that a lot. And I did in this project. And it is the interest is really appreciated.
I find even myself, because I feel very both inspired and overwhelmed a lot of time. It's not to say that I don't find myself intelligent. It's just that I'm I've surrounded myself with some really brilliant minds, and I see what other people do, and I say this not for the benefit of anybody other than maybe our younger listeners who come up to me and talk to me about this stuff, but just know that I find myself all the time thinking about, oh my God, I can try and do this. Can I do this? Should I say that I can do this? And I would say also that if I enter a new project, something maybe I've never done before, which is always, especially in consulting, you're always doing something new. But it's really about leaning on the people around you too, because I've yet to meet a geochemist that has been selfish with their knowledge. So if I have a question about something because I don't understand who knows what it is or whatever, I just call up the phone. And it's this really great community of people that we have. And I think that in your honesty just now, and perhaps even my own, I find that will help inspire people, because whether they have a failure right now to have a job, because it's always difficult to get a job, or they are stuck somewhere in view of maybe that they want to pursue geochemistry, but their professors maybe don't really think that's the way for them to go. There's all these things, and I've been privileged in the last few years with the amount of people that I've encountered that have shared their own stories, but I don't think to this point that I've really heard somebody with as much experience as you share something like that. I think that's a privilege for everybody to hear. So thank you.
Probably more common than
Yeah.
confessed, but I would just say that you should always see the potential in people. Really, it's about having the time to invest, to backfill any deficiencies in knowledge and figure things out. And also, if maybe you don't have all the numeracy that you need to do certain calculations, you don't have computational skills, there's a lot of simple calculations. And I would just say, I think we've quantified a lot of elements around a magmatic system here that wouldn't otherwise be quantifiable with just the simplest of mathematical expressions. And this is a guy, a heat flow specialist here at the University of Utah, David Chapman, who used to always come up with the most eloquent lectures that made geoscience sound so accessible, because you could just use simple mathematical relationships to get a first order quantitative understanding of systems. And those pathways to characterization and problem solving exist, and they are an asset. And really, geologists and geochemists, we draw on diverse data sets to interpret what we're working on. Many of us do. Those are important things.
I want to thank you for being here so much and being so raw with us at times too. I think it was, now I'm going off script, but I think it was a huge thing for all of us to hear, especially somebody that to the surface has such a storied career with so many publications and leading the fields in geothermal and epithermal research. So I want to thank you for being here. Thank you for sharing your story. I hope everybody, all of our listeners, enjoyed it as much as I liked learning about all the different things, particularly about geothermal, which I have not worked in ever. So this is cool. Thank you everybody for listening to Geochemistry, and a big thanks to Stuart Simmons for being on the show, dishing some tea and talking about geothermal geochemistry. Thank you to your sponsor, LKI Consulting, to It's Water and Coma Media for our music. And I'm looking forward to chatting with everybody next month.
Thank you. Yeah, that's great. I really appreciate the opportunity.